Thank you for being here this morning. It's my pleasure to be here. I'm an experimental psychologist and a member of a small and dedicated group of psychologists known as ecological psychologists or Gibsonians. And much of what we have to say is best understood and best described by comparing it with sort of more traditional cognitive science. So let me start with a little overview of what I'm going to talk about today. I'm going to first present a problem for you, a perception action problem, and ask you to think about how you would solve it to help you decide whether you're, by the end of the talk, more ecological or more traditional cognitive in your approach. And then I'm going to draw some distinctions, 6 distinctions, if you will, between the ecological approach and the more traditional approach. And I'm going to frame that as 6 principles of ecological psychology. The first 5 of these I'll go through fairly quickly, and then the last of them concerns learning, and that's where the majority of my attention will be given this morning. So, let us start with the outfielder problem. Okay, I know you're Europeans, mostly, but imagine you're standing, one can make a football analogy out of this, but imagine you're standing in center field and a ball is hit by a batter and flies in your sagittal plane. This is the most difficult for a new learner of baseball to catch. Okay, it flies just in your sagittal plane. You're going to see part of the trajectory and eventually adjust your activity so that you intercept the ball. So now the question is, how do you do that? Take 3 seconds and think about if you were to try to explain this as a scientist. Now, this problem has been around for some time now, so perhaps you're already familiar with the ecological approach. But if not, think about what sorts of processes you imagine would take place in catching the ball. The usual response that one sees from cognitive psychologists is that you watch the first part of the trajectory, and that is followed by certain mental processes. I've got this bubble, thought bubble labeled here. And usually the goal of what's happening in the bubble is an extrapolation of the trajectory of the ball. The details of what goes on in that bubble will differ, but you extrapolate the trajectory of the ball, figure out where it's going to land and when it's going to land, and then guide your motor activity accordingly. So what goes in the bubble? Well, different theorists would come up with different things. Processes in the cortex, say, or models of gravity, memory, sensory integration, binocularity, even auditory system, and of course, computation. So the problem then is really divided up into perception and prediction of the future, action planning, and then execution of the action. Now, as I discuss these 6 principles, I'll be sort of describing a different kind of approach, the kind of approach that would follow from the ecological view, and one that would be very different from this characterization that I've just presented. Okay, so 6 principles. The first principle is animal-environment mutuality. And here the claim is that one ought not separate animal and environment in trying to solve problems in psychology. Okay, problems of perception, say. I'm fundamentally a student of perception. And the more common view is of animal-environment dualism, that cognitive psychologists really worry very little about the environment and concentrate on what's going on inside the animal's skin. They therefore tend to describe the environment in animal-neutral terms, not sort of worrying, just standard physics. So if you want to talk about characteristics of the environment, you might measure size with a ruler or mass with a scale. And in terms of the information to which your sensory systems might be sensitive, again, let's borrow the metrics from physics. Light is about wavelength, number of photons, etc. The ecological view, in contrast, is going to try to describe the environment in animal referential terms. Now, the most important of these is affordances, and this is perhaps the most famous concept that has crawled out of the ecological view and become a mainstream concept, although I must tell you that many people use it in a way very different from the way Gibson originally used it. And of course, he actually coined the term. But affordances are the actions permitted by some object, event, or place in the environment. And those are animal-specific. What affordances, what this object affords me would be very different from that which affords a child or a squirrel or, at this university, a feral cat. Similarly, in information, we're going to seek a characterization in terms of richer, higher order patterns. We're not going to be bound simply to local luminance levels, but to look for patterns both over space and over time. Okay, so what do affordances look like? What does it mean to measure in terms of possibility of action? A couple of quick examples. We might measure an aperture, so rather than simply talking about the size or shape of an aperture, we'd say that that aperture can be walked through. That would be affordance of this doorway. Similarly, rather than talking about the height of a staircase, we might describe it as a step-down place, okay, and not concentrate on traditional metrics like distance. And similarly, a ball might be graspable rather than, or throwable, rather than, weighing 200 grams and having a diameter of, 12 centimeters. Okay, so now as we go back to the baseball batting example, right here, our first principle, animal, environment, mutualism. These two things go together. Let's not separate them. What does that mean for baseball batting? Well, it's going to be that the information, the task, we really want to describe it as about the ball catcher system. It's not about the ball and its trajectory, followed by some separate animal process, like route planning, but instead, the optics that we might be sensitive to might be about your relationship to the ball, and it might tell you exactly what to do to catch it or to intercept it. Okay, let's move on to principle 2, and that is the specificity of information. In the ecological view, it's emphasized that there's a one-to-one relationship between optical patterns or acoustic patterns and objects and events in the environment, or affordances in the environment. And traditionally, psychology and philosophy have emphasized a many-to-one relationship, where there can be any sort of shape out there, and it doesn't tell you about what the distal object is like. It doesn't inform about it. So, for example, image optics best characterizes the traditional study of the light to an eye. Let's look at the characteristics of a retinal image, for example. Ecological optics, in contrast, is going to emphasize higher order optical patterns that are specific to properties of the world. Okay, why is this important? Well, where you stand on this issue of specificity sets the stage for your theory of perception. If you assume that the input is a static, two-dimensional image, a standard retinal image over time, there are various problems with it. Those problems include that it's upside down and backwards. People have worried about that. That size, distance are distorted, and shape. What's meant in this, to be demonstrated in this picture is that, trapezoids and squares that are far away or close up can all yield the same image on the retina, a many-to-one relationship. Now, if that's your starting point, and we know what your ending point is, that you look up here and see me to be a normal-sized person in 3 dimensions, and so I depart in a variety of, your experience of the world departs in a variety of ways from image properties. So this is what your theory is going to have to solve if you start with non-specifying information. How do you get from things like this to things like this? Okay, from the ecological view, and let's now turn our attention back to baseball catching, what we would notice about the optical patterns that accompany this baseball flying at you in the sagittal plane would be that if your eye, and that at point B is meant to be your eye, is at the location that the ball will arrive, if you're already in the right place, the optical pattern that you will see is of a ball basically rising on the image plane at a constant velocity. Okay? So constant velocity, that means you're in the right place. If, on the other hand, you are standing in front of where the ball will land, the resulting optical pattern will be accelerating on the image plane, and conversely, if you are behind where the ball is going to land, the ball will decelerate on the image plane. Okay, so if you're pointing to it, it starts to slow down. So these higher order patterns, if you will, inform of where the ball is going to land. So this presents a very different problem for a theory of perception if you're worried, or a theory of catching balls, than, let's say, a succession of static retinal images. So this pattern of acceleration. Okay, we'll come back to this. But for now, let's turn to our third principle, and that is perception-action mutuality. The history of psychology has been marked by a separation of these, but for the ecological view, perception and action go hand in hand. The point of perceiving is to guide activity in the short term and the long term. Traditionally, though, these activities have been separated. Perception is seen as a process that precedes action, and action follows, and indeed, knowledge and representations become the end point of perception and the starting point of action. From an ecological view, we are going to notice several kinds of relationships between perception and action. For example, the importance of exploration creating information. Okay, you can obtain information through exploration, that our execution will reveal information, and that attending to this conjoint relationship, perception-action mutuality, will make us think about looking for information that in fact guides our action. So now let's put this back in the context of baseball catching. So the traditional dualistic view was the story we saw a few moments ago, perception of time and place of landing, appropriate action planning, and execution. Whereas when you start to exploit optical acceleration, as information, a new possibility obtains. Namely, that relationship that we looked at here holds in a variety of circumstances. It holds if you are standing in the right place. It also holds, in the second case, if the ball is just going straight up and down and you are running at the right speed. It holds if the ball is moving forward and you are running towards it. And it holds, finally, if the ball is going behind you and you are running appropriately. So if we put that all together, this would suggest a way of controlling locomotion in ball catching. Namely, run in such a way as to cancel out this optical acceleration. Okay? That will lead to, if you are successful in doing that, that will lead to an intersection of your eye path and the ball path. So you will apparently solve the problem of where to be and when to be there without knowing either, right? There's nothing about time here. There's nothing about place. It just says, use this style of control, adjust your ground reaction forces or the ground reaction forces that are created proportional to the acceleration in the optic array, and you will get to the right place at the right time. Okay. Our next principle is direct perception, and that simply argues that perception is the pickup of information. And of course, information as defined earlier. The more traditional view, of course, is that perception is an inferential process, computational, and memorial. And in part, that's dictated by this information that we started with, that this insufficiency of a traditional stimulus. So because the retinal image is ambiguous, perception must involve these kinds of processes. From our perspective, though, because information is specific to important environmental events, and specific, for example, to how you should be running, then your job is to basically let that information control your locomotion. Not to store, not to compare, not to retrieve, not to predict, not to anticipate, just yield control to the appropriate information. Another key feature of, I'm going to skip that. Another key feature of direct perception is the idea that you sort of pick up information in a single step. And I'm going to just briefly mention a couple metaphors for this, because sometimes it's difficult to intuit what it might mean to just directly measure a higher order property. And a metaphor introduced by Sverker Runesson, a Swedish psychologist, said we should think about perceptual mechanisms as smart perceptual devices, okay? And he used as a metaphor for that a particular smart device. Here's the problem. You want to determine the area of a rectangle. How to do that? Now, our usual inclination is to do the sort of traditional cognitive psychology thing. Measure lower order variables, length, width, and then take out our calculator and do a computation, and we get the result. But in Runesson's metaphor, namely the polar planimeter, you have a device that engages in an activity that will ultimately measure area without measuring length, without measuring width, and without doing computations. Usually, they're used for measuring irregularly shaped objects, and what you do is simply trace the pole end is planted, and then you trace the lens around the perimeter, and when you're all done, you have measured area, and you can read the measurement off the dial. So it measures area directly, without measuring lower order properties, without doing calculations. And of course, we could use it as well to measure a rectangle. Now, notice, however, that if you're sure that the way to measure the area of a rectangle is to measure a length and a height and do a calculation, you're going to be in trouble here because you discover that this device is really bad at measuring lengths. It's, it gets, the dial will move, but you won't have a good basis to start. So a device that measures area measures a higher order property without measuring lower order properties and doing calculations. So think of that as sort of the way an ecological psychologist would think that a biological information detection system works. A second metaphor that I won't describe in any detail, but just sort of mention it here, is of resonance. And what resonance is all about is simply that maybe we should think about cognitive systems working more like radios than computers. Okay. Let's turn our attention now to the fifth principle of ecological psychology, and this I will sort of generally label as a commitment to physical science. And what is meant by that? It's not reductionistic, let me say that to start with. We believe that phenomena in general are to be understood in terms of laws and circumstances, or boundary conditions, initial conditions. And so our job as psychologists is to identify the relevant natural laws.